Okay, so welcome back, everybody. We should probably restart the final session of the workshop. So we will have a talk by Biagio first, and then the further discussion on the white paper. So without further ado, I will leave the stage to Biagio, who is going to talk about ergodic sampling with the density of states.
Okay, so thank you, Luigi. It's a pleasure today to talk about this program that we have in collaboration with many colleagues.
We cannot hear.
Yeah, we cannot hear.
L'abbiamo provato prima, ok. Dov'è il posto? Vedi un po' se lo trovi. Stop. Ecco adesso. Okay. Is it better now?
Yeah, much better.
Okay. Okay, very good. Thank you very much. So as I was saying, it's a pleasure for me to talk today about this program that I'm doing in collaboration with several long-standing collaborators, and the list is growing. I will make them justice as we proceed as much as we can. So the problem we moved on is starts from importance sampling. Importance sampling is what we use the most in lattice gauge theory, and it has proved to be very successful. However, there are cases in which importance sampling is not efficient or spectacularly fails. For instance, a phase transition, which is one of the subjects of this workshop. If you are on a second order phase transition, there are correlation times which diverge as you approach the critical point. It was the critical slowing down that Dimitrios was mentioning this morning. Or even at first order phase transition, you get two equilibrium state at the phase transition with an exponentially suppressed time to sample them. So the question is how we can bypass these difficulties. And for that, I will propose a technique based on the density of states, which is not a traditional Markov process, and then doesn't suffer from the correlation, typical correlation or suppressions that we find in the Markov processes. So the algorithm is called LLR. We stay for linear log relaxation, and we will see why shortly. The outline of the talk is very simple. We will start with the algorithm for real action system, where everything is under control, and then I will show applications from systems with complex actions. And finally, I will conclude and we'll see what else is left. So let's start with the real action system. Let's write a prototype partition function for a system which has degrees of freedom that I have indicated with phi. The partition function is obtained as the path integral, if you prefer to use the language of quantum field theory, is obtained by integrating over all possible configurations the Boltzmann weight, which is given by the exponential of minus the inverse temperature times the action. We can now rewrite the partition function by defining the density of states. So the density, how many states essentially contribute to the integral once I fix the value of the action to some value e. So if I insert this function rho e in the partition function, I can rewrite it as an integral over the density of states itself of the Boltzmann weight. This is about page 2 of any statistical mechanics book. So I'm not saying anything particularly profound at this stage. What it is important is that if I know the density of states, any observable which depends on the action can be written as a numerical integral in the formula that is shown here at the bottom of the slide. So it's a semi-numerical integration that in principle can be performed. Now, the question is, am I just rephrasing the problem, a difficult problem, in an impossible one? After all, we know that the density of states goes exponentially with the number of states. I mean, as we increase the temperature, for instance. Well, the point is that in the early 2000s, progress has been made in the computation of the density of states through algorithms that look like bias random walk in density of state space. The most popular one, but not the only one, is the Wong and Landau algorithm. And by taking inspiration from the Wong and Landau algorithm, we have proposed the following method. So the method goes as follows. So essentially, we divide the possible values of the action in intervals of amplitudes delta E, and we restrict to the single interval. However complicated the density of state is, we assume that its logarithm, so what microcanonically will be the entropy, is linear in the energy itself. So this is a first order Taylor expansion, so, which I can write in this way. So I'll take the part which depends on the energy plus some constant, which I will discuss later on. Now, if you look at this coefficient AN, this is very physical because it is the derivative of the entropy with respect to the energy. So as such is the inverse temperature. So what I'm doing here is I'm parameterizing with the local inverse temperature the density of states. How do I obtain this coefficient? Well, I know that if I sit at the center of the interval and I compute an integral which is linear in the energy, like here, I mean, just the expression that defines the variable for the density of states. If the density of integral is exactly the one that I've parameterized, then the exponent here, this term rho v e to the minus a of n e cancel exactly. So this will be an integral over the flat distribution, so it will be 0. If I put an arbitrary a, the integral will not be 0. So what I'm trying to do is to tune a so that this integral becomes 0. How do I do that? Well, you know that if you have an equation, you can use efficient methods to solve them numerically. For instance, the Newton-Raphson method. The equivalent of the Newton-Raphson method for a stochastic equation is the Robbins and Morrow method, which is not that dissimilar. So what you do is you build a sequence and you correct by the first derivative and the value of the function. But the sequence is suppressed with the terms which depends on the value of the number in the sequence that you have. The suppression terms has to fulfill properties, so it has to be not summable, but the square must be summable. So the easiest sequence that satisfy this property is 1 over m. So we use 1 over m. Alpha is an arbitrary coefficient that one can tune. And actually what one finds is that if you choose alpha in such a way to minimize the variance, you will reproduce exactly the term that you will put from the Newton-Raphson. Okay? So this is the stochastic equation that we solve iteratively. And what it has been proved is that at fixed m, you have Gaussian fluctuation around the n. So rather than to solve by making m go to infinity, we essentially go to recursion large enough and we solve different series, and then we compute the average over all the findings. The coefficient Cn is then tuned by imposing that the density of states here is piecewise continuous. So this is a very simple algorithm that we have proposed first with Antonio is in the audience and with Kurt Langfeld in 2012. And there we solved the equation with the Newton-Raphson method. The improvement that we did in 2016 with Roberto Pellegrini, which actually suggested the method to us, was to use the Newton and Raphson. And this proves to be crucial. Here I'll give you some examples from the original paper. An advantage of this algorithm that I don't have the time to prove today is exponential error suppression. Exponential error suppression means that the value delta rho over rho is constant, no matter what the value of rho is, the absolute value of rho is. This enables us to determine rho over several orders of magnitudes, And here I've given a demonstration. We provided a demonstration on the paper when we proposed the method in 2012. You will see, for instance, that for SU2 gauge theories, we determine with good accuracy. I want to remark that these lines contain the errors, the statistical errors. We determine with good accuracy over 120,000 order of magnitude, the density of states. And for SU2, and with SU3, we managed to go to 150,000 order of magnitude over all the space of normalized action. Of course, I mean, this is meaningless unless you compare it to Monte Carlo data, and the comparison is on the right for SU2 and then for SU3. And as you can see, the points go perfectly to the line. If you zoom in, the error are of the order of 10 to the minus 5, which is the typical error that you get on the plaquette anyhow when you do a Monte Carlo calculation. So we are competitive and in fact precision below the Monte Carlo calculation. Now, the question is, how does the method perform around phase transitions? So first of all, how do we see phase transitions? So we have taken an historically particularly challenging phase transition that has kept the community busy over a number of years to establish, for instance, its order. And this is the 4-dimensional U1 lattice gauge theory transition, which is first order for beta around 1. So what we did is we applied the density of state method for beta around 1. And we came up with this determination of the inverse temperatures as a function of the energy. I want to remark here that the function is non-monotonic, and this is the sign when you invert it that there is a phase transition. Okay? So when you go to infinite volume, as you will see from the zoom over here, the non-monotonic region gets flatter and flatter. So you will get this flat region, which will indicate a phase transition. Yeah. So we went up to lattice 20 to the 4. The standard in this determination with periodic boundary conditions, which is the case that is more challenging, was 18 to the 4, and this was done in the early 2000s using the best supercomputers available then, and in a calculation that took a number of years, 2 or 3 years, by the Wuppertal group. And what I'll show you here is a determination done on the 20 to the 4 lattice, so the new state of the art, essentially, where we have also shown that we reproduce the norm value with better accuracy. And what I want to remark is that this has been obtained over a number of weeks, 2 to 3 weeks. Now, true that we have had lots of progress in the Moore's law, but I can guarantee that this is not just Moore's law. The algorithm is efficient at overcoming the transition. And in fact, we have at least numerical evidence, and also we have arguments, analytic arguments that say that the scaling of the algorithm is polynomial at the phase transition. Okay. There is one aspect that I have not covered, so I'm restricting Monte Carlo sampling in interval. How I am sure that I'm actually satisfying ergodicity? There are a few ways, and one is the replica exchange method. So what I'm doing here is I'm starting 2 sequences. One sequence goes with my established number of intervals. The other one is displaced by half the interval, so that each interval of the top sequence will overlap with for half with 2 intervals in the bottom sequence. So what I can do now is whenever I have 2 energies in the 2 values of the configurations, or 2 configurations in the top and bottom sequence whose energies overlap, then I can propose an exchange between the 2 replica. So I can put the configuration at the top in the bottom and vice versa. And this is given with a simple metropolis probability, which is given down there. So this satisfies detailed balance, so restores ergodicity through the replica. The other characteristic that I want to remark is that you don't need to simulate the whole interval region. This is because you know that as you increase the volume, the partition function peaks. And you can close the replica far away from the region of interest with the standard Monte Carlo. okay, with standard acceptance Monte Carlo. This is known, for instance, to people that are using the multi-canonical. So this is an example of the deconfinement phase transition in SU3. This is work in progress that we have started. The lattice is very small. This is at the beginning. The very reason I decided to present this was the talk that Francesco gave on Tuesday. Francesco Sannino showed us how important it is to determine the latent heat of the transition. And we also know that the latent heat of the phase transition in pure gauge SU3 is a particular difficult observable because it suffers from very heavy corrections with the lattice volume and with the lattice spacing. So we thought that we could use this method for this transition and for the other gauge groups. So on the figure on the left, you get the reconstruction of the probability densities in the 20 to 30 cube times 4 lattice for SU3. The phase transition is given by this curve that is non-Gaussian, which is very hard to simulate. So what we did is we simulate in a region of beta round, and there are two lines here that you can see. One line is from a standard Monte Carlo simulation, and another one is from the density of states. Except for details, they are virtually indistinguishable. And the curve that you see on the right is the specific heat, this time extracted from this density of states, just by a simple numerical integral with the Boltzmann weight. So the goal here will be to go to larger lattices to see a clear distinction between these two peaks and to determine the latent heat that way. There is another way that we have to implement ergodicity. This time we still do replica, but rather than have an hard cutoff, so by cutting the interval, we use a Gaussian cutoff. This is a method that Antonio suggested to me, in fact, and we have used for a calculation that I'm going to show. But what I want to remark here is that a good property of this method is that you can implement it quite easily in hybrid Monte Carlo. So it could be, in fact, a first step at introducing fermions. So in this case, what we did is we studied the topological charge in SU3. Topological charge is a particularly difficult observable because it has very long correlation times as you approach the continuum limit. And what we did is we used the strong coupling as a reservoir for changing topological charge. So essentially, we built a sequence of these values of energy that interpolate between betas that are in the region of 5.7 when we have no problem at all the way to beta in the region of 6.2. So this is how you see how the configuration moves across the replica. So we made sure that essentially all the configuration visited a relevant number of replica, at least half of them. And this is a calculation of the correlation times, where you can see from the points here determined via Monte Carlo, you will see the correlation time that diverges as you approach the continuum limit. Well, you'll see that the correlation time determined with our density of the state method, well, it doesn't show sign of divergence. That perhaps could be a little bit optimistic, but it's certainly an order of magnitude below the correlation time of the important sampling method. And this has been done in a recent work with Antonio, Roberto, David Lancaster at Plymouth, and Guido Cosso, who started this work when he was in Edinburgh. So this is the state of the art. This is a very quick overview of what we have done with the LLR algorithm, which once again, the property of the algorithm, the key property of the algorithm is that implements exponential error suppression. So we can visit hundreds, thousands, and hundreds of thousands, in fact, orders of magnitude of the density of states without appreciable deterioration of our states. So can we use, what we ask ourselves is, can we use it to brute force a very difficult problem such as the same problem? Okay. And this is the second part of the talk. Now, let us revise quickly what is the same problem. So in the same problem, we have a partition function, which this time depends from two couplings. One of them coupled to the real part of the action, but in addition, we have a coupling to an action which is imaginary. Okay. So this is what is called the same problem, because we lose here the interpretation of the partition function as of the measure as a measure in the proper mathematical sense, and so we cannot do the standard importance sampling. Okay, I need to rush because Luigi he tell me that I just have 5 minutes. So let me move on. So here what we do is we introduce a generalized density of states in which we want to expose the observable that couples to the coupling with the imaginary part. And we do Monte Carlo to determine this rho of Q. And we determined once again using the density of states. Here I want to remark that I cannot use any longer the piecewise approximation that I've used for the continuity of the density of states in the previous case, because that would disrupt the exponential, the Fourier transform, and I will see just the singularities of that decomposition. So what we do is we interpolate smoothly the density of states using a polynomial. The other remark that I want to make is that this is not the LLR method. The LLR actually is the extraction of the density of states. What we do with it is something else. So the extraction of the density of states is controlled and controllable. The interpolation is the part that needs further thoughts. And here I give you some demonstration using the Bose gas, which is a problem that one can solve, for instance, in Millfield. It has been solved in Langevin and in several other ways. And here we give you the extraction of the density of states for a particular value of the volume and a particular value of the chemical potential. These are the typical figures that we obtain. So on the top left, you see the density of states. On the top right, you see the sign, the average value of the sign, which tells you how challenging the problem is from the numerical point of view if you do it brute force. And then the sign is related to the overlap free energy, which I plotted on the left, and on the bottom left, and on the bottom right, there are the various polynomial interpolation. As you'll see, the polynomial interpolation are under control for low mu, and this could be expected, and they start to be less and less under control as you go to higher mu, and they start to be also less and less under control as you increase the volume. Anyhow, for this particular problem, we can still do all the calculation, and we especially were able to extract the overlap free energy in the low density phase, and this turns out to be in agreement, but with visible deviation from the mean field calculation, which is due to a paper, which is reported in a paper by Hert. Okay, so I'm at the end of the talk. So what I think I have convinced you is that for system with a real action, the LLR algorithm has advantages over traditional importance sampling. In cases in which you get a signal that is exponentially suppressed, for instance, over the volume, or you have very large correlation times, or even multiple states with the exponential barriers with the volume between them. For the case in which we have a same problem, we have a number of models in which we have been able, through numerical manipulation of the density of states, to obtain numerical results for this problem. So what else can we use the system for? Well, one of the applications that come out of this workshop and is gaining momentum anyhow is finding signature from early universe phase transitions. This could come from QCD or could come from models of dark objects. And the method here provides a good approach to those systems. We want to generalize it to system of fermions, but the real ambition will be to have a proof of concept solution of the same problem in QCD, even on small lattices. And thank you very much for your attention.
Okay, thank you, Biagio. Very nice talk. We'll take questions from the audience first and then look on Zoom. So any questions here in the room? I don't see any. Maybe I'm going to ask you one, Biagio. So what are the, Uwe Jens, you go first and then I'll ask mine.
Yeah, thank you very much for the nice talk. You say that you were able to solve certain sign problems. What do you really mean by that? I mean, the sign problem is exponentially hard.
Yes.
And if the volume increases, I would suspect that you eventually run into problems, but maybe the sign problems that you could tackle were not so severe. Is that the case?
Well, not necessarily. What I mean is that there is an intermediate region in which I have my numerics under control, and that region enables me to interpolate. What you refer to is you probably refer to the fact that the value of the sign, as I'm showing this slide, is the ratio of two partition functions, which goes exponentially with minus the volume, the free energy of the overlap. What I mean is that I was able to extrapolate the free energy density of overlap, and so that I know the same problem. I mean, I know, for instance, this expectation value of the sign at any volume, even where I've not done the simulation. And I expect that to carry on to other observables.
So the values of the sign that you could handle, how small were they at the end?
Well, we were able to handle signs which was of the order of 10 to the minus 480.
Okay.
Which is not infinity, agreed, but it's still rather impressive, in my opinion.
Yeah, that is impressive. If I understood it correctly, you say 10 to the minus 480. Is that what you said?
Yeah.
Okay.
That was for the Bose gas. I'm also not claiming that all the systems are the same.
Thank you.
Well,
okay. Any more questions? Tim.
So naively, I suppose this sign problem, I mean, is somehow a problem of large cancellations, trying to solve these large cancellations, which is, I mean, so of course, signal to noise ratio problems are somehow related. Do you, I mean?
Well, the idea is that if I'm able to do the integrals sufficiently precisely, and I'm able, I mean, I know that there are a lot of ifs here.
Yeah.
If I can do the integrals, all the integrals that I've shown with infinite precision, and I'm able to interpolate it with infinite precision, then I just need to do a Fourier transform that I can handle numerically. Okay, so that's the claim.
Is there any practical signal to noise problems?
Well, it's an asymptotic question, which also depends on the system. So we can bound rigorously, we can bound the sign. We know what to expect for the precision. Then the question is which level of precision we need in the data and which level of precision we need in interpolation. In the data, the algorithm can get to, if you run it asymptotically, it can get you to the perfect solution. So you will need to interpolate the data. You need to get a number of coefficients to a given level of precision, and then to get also the interpolation in between them to a given precision. And that's it's highly problem dependent. We were able to do on the 5 to the 4, and that was, it took a certain effort, but it was feasible.
Thank you, Biagio, for the very nice talk. Really appreciated it. I have two questions related to the reduction of the autocorrelation time in the FC3 H theory.
Mhm. Well, our is not a traditional important sampling. I mean, it reduces everything to a flat sampling essentially. So that can help. And the other thing is that, of course, we have given you the summary, but the details are pretty much nuanced on how you do the, I mean, you know, what needs to be done for the analysis of the autocorrelation time. If you want, we can have this discussion, but the paper has a very long discussion on how to extract the autocorrelation time. It's not naive. You know, the details are pretty much nuanced there. Well, we think that they scale polynomially, pretty much like everything, but I mean, you know, we cannot prove it, and certainly we will not be making this claim officially. It's actually, I mean, you know, I wouldn't be surprised if at some point you see just the exponential scaling again, with a small pre-coefficient. Or what I can tell is that here we gain 1 order of magnitude. So that's the most solid thing, the most solid conclusion that I can draw.
Okay, any more questions? I don't see any online, so I think this is the end of the sort of scientific program. So let's thank Biagio and all the speakers again.
Thank you.